Hi everyone, welcome back to the math tutor. In today's video, we revise equivalence relation and learn about equivalence classes, quotient set and partition of a set, and also do two important theorem on equivalence class. So, if you found this video helpful, make sure to subscribe and hit the bell icon to never miss out any of my future video. So, let's come to the topic. Partition equivalence relation. Equivalence relation. We learned in our previous video that is any binary relation on a set A is said to be equivalence if it satisfies three properties. Okay, what are reflexive, symmetric, and transitive. Okay, so any relation on a set A, suppose R is defined on R is a relation on a set A. So what is reflexive property? If for any A belongs to A, if A related to A, we say relation R is reflexive, and for any A and B belongs to A, if A related to B implies B related to A, then we say it is symmetric. And the third one, transitive, is if for any ABC belongs to A, if A related to B and B related to C, then this implies A related to C. So if any relation satisfies three properties, that is reflexive, symmetric, and transitive, we say that relation is an equivalence relation. For example, equality is an equivalence relation. That is, suppose I define a relation on A where every element is equal. Okay, so it is clear that A is equal to A, which satisfies reflexive property, and I can say if A equal to B, that implies B equals to also A. So it is symmetric. And for transitive is also obvious that if A equal to B and B equal to C, that implies A equals to C. So equality is an equivalence relation. So I have a question for you. Check whether less than or equal to. Okay, I have defined a relation on a set A where A is less than or equal to B. Check whether this is an equivalence relation or not. Check it. Okay. And comment. Now we define equivalence classes. Equivalence classes are generally sets. Okay, so suppose the symbol, okay, denote an equivalence relation. Okay, on a set A. Now, the equivalence class of any element A belongs to A is the set A bar consisting of those x belongs to A which form equivalence relation with the A. Okay, you understand with an example. Suppose, sorry, I have it, and I have a note here that the set of all equivalence classes is called the quotient set. The quotient set of A modulo congruent, or we can symbolically write this as A mod congruent. Okay, so this is the actually set of all equivalence classes. We understand with an example that every set, any set, can have more than one equivalence class. So the set of all equivalence class is called the quotient set of A modulo that congruent relation. Okay, so for example, I have a set A where I have 1, 2, 3 up to 10. Okay, and I am define relation which is collection of all order pair AB which belongs to A cross A, where A minus B, A difference B is divisible by 3. Okay, so check this also is whether this is an equivalence relation or not. Check for equivalence relation. Check for equivalence. Check for equivalence relation. Okay, so it is actually equivalence relation. Just verify it. Okay, so we found the equivalence classes here. So suppose what will be the equivalence class of 1? So here the relation is equivalence relation is R. So every element of the set A where those are satisfy the equivalence condition with the element 1 are in the equivalence class of. For example, suppose equivalence class of 1, I can write equivalence class of 1 is equals those B belongs to A such that 1 minus B is divisible by 3. Okay, so this is the equivalence class of 1. So which elements are make the equivalence will be in the equivalence class of 1? Okay, we check from the set 1. Okay, the difference of is the collection of all B, okay, are in the equivalence class of 1, where the difference of 1 and B should be divisible by 3. So we check from 1 minus 1 is 0 is divisible by 3, so here it comes 1. Now 2 minus 1 is 1, which is not divisible by 3, so 2 is not in the equivalence class. So 3 minus 1 is 2, it is also not divisible. So 4 minus 1 3, so 3 is divisible by 3, so 4. Now 5, okay, 1 minus 5 that is 4, or 1 minus 5 that is minus 4, which is not divisible by 3. Similarly 6, 1 minus 6 which is minus 5, that is also not divisible by 3. 7 minus 1 6, which is divisible by 3, so 7. And 8 minus 1 not divisible by 3, 1 minus 8. Then 8 minus 1 or 1 minus 8? Since it is an equivalence class and every element are making equivalence relation with one, so by symmetric property I can write 1 minus b or b minus 1. Okay, both are the same thing. So 9 minus 1 is 8. 8 is not divisible by 3, so 9 is not in the equivalence class of 1. And at last 10. 10 minus 1, it's 9. 9 is divisible by 3, so 10 is also in the set of equivalence class of 1. Similarly, equivalence class of 2, how I can write? It is also the set of all b belongs to a such that 2 minus b is, or b minus 2 is divisible by 3. So the elements are 2, 2 difference to 0, 0 divisible by 3. Similarly, 5 difference to it's 3, 3 divisible by 3, and 7. Okay, and other are not will be in the set of equivalence class of 2. Okay, and now equivalence class of 3 will be, it is obvious 3. Okay, 3 difference 3 is 0. Similarly, 4, 5 cannot, for difference of 4, 5 and 3 is not divisible by 3, so 4, 5 are not in the set. Then 6 and 9 are also in the set. Now if I try to find the equivalence class of 4, okay, that the difference of element of a and 4 is set of elements which difference of 4 with the elements of the set, okay, are divisible by 3. So I found that it is equals to the equivalence class of 1. Okay, now let's take it. Okay, if I found the equivalence class of 4, I found those b belongs to a such that 4 difference b is in the equivalent is divisible by 3. So 1 for the case 1, 4 difference 1 is 3, 3 divisible by 3, so 1 is in the set. In the case of 2, it is not possible. 4 difference 2 is 2. In case 3, it is also not possible. In case 4, 4 difference 4 is 0, 0 divided by 3, so 4 in the set. Similarly, 7, 4 difference 7 is minus 3 divided by 3, so 7 is in the set. And for 10, 10 difference 4 is 6 divided by 3, so 10 is in the set. So it is same as the equivalence class of 1. So here comes a theorem that if any element x belongs to the equivalence class of some a, then equivalence class of x is equals to equivalence class of the set A. Okay, so this is a theorem. Okay, we prove this. So I am writing the statement. Okay. So if you try to here also, if you try to find the equivalence class of 7, it is also equals to the equivalence class of 1. And if you try to find the equivalence class of 10, it is also same as equivalence class of 1. Similarly, if you try to find equivalence class of 5 and 7, it equals to equivalence class of 2. Similarly, equivalence class of 6 and 9 is also same as equivalence class of 3. Okay. Verify it. Okay. Verify and comment. And comment. Now we have a theorem. Let the symbol, this denotes an equivalence relation. This symbol is generally called as tilde. Okay. Equivalence relation. On a set, it is an important theorem on equivalence class. Okay. And let A belongs to A, let A belongs to A, then for any x belongs to A, then for any x belongs to A, x is congruent to A, sorry, x form an equivalence relation with A if and only if equivalence class of both are same. Equivalence class of x is equals to equivalence class of A. So here one is congruent form an equivalence relation, congruent, so I am saying congruent, but it is that one is forming an equivalence relation with 4, one is forming an equivalence relation with 7. So if that condition arises that if x is form an equivalence relation with A, then equivalence class of x and equivalence class of A are same, which shows the example that since equivalence class of 4 and 1 are form an equivalence relation with each other, so their equivalence classes are same, hence their equivalence classes are same. So we prove this theoretically. Okay, so here we show that these are clear, it is clear that these are sets. Okay, equivalence class of x is a set and equivalence class of A also a set. So to show the equality of two sets, we have to prove that both sets are subsets of each other. Okay, so when A set is equals to B set, it is possible only when A subset of B and B subset of A. So we have to show this condition. So what we have to show here? We have to show here that x equivalence class of x is subset of equivalence class of A, and equivalence class of A is a subset of equivalence class of x. Okay, so first we have to prove that equivalence class of A, let x is congruent to A. Okay, so congruent, I am saying congruent, but it is an equivalent relation. X is equivalent to A. Okay, x forming an equivalence relation with A. And here we have to show this first we have to show x equivalence class of x is subset of x equivalence class of A, and then in second we have to show this we have to show this. Okay, equivalence class of A is subset of equivalence class of x. So to show the first condition, let I am taking an element, let some y belongs to x. Okay, x bar equivalence class of x. That implies that y is form an equivalence relation with x. It is clear from the definition of equivalence class that if any x belongs to A and x in the equivalence class of A, x is in the equivalence class of A, that means A each form an equivalence class with the x. So if y belongs to equivalence class of x, then y is form an equivalence relation with x. But also we have that x is form equivalence class with it, but also we have x is equivalent with A. So since this is an equivalence relation using transitive property, okay, y related to x and x is related to A, that implies y is related to A. Since y related to A, it is a by transitive property. Okay, by transitive property. Since y related to A, that implies y belongs to equivalence class of A. Okay, so this proves that I am taking an element of X and shows that y belongs to equivalence class of A. Okay, I am taking an element in equivalence class of X and found that element is also belongs to equivalence class of A. So every element of X is an element of A bar. Okay, every element of X bar is an element of Y bar. This implies that equivalence class of X is a subset of equivalence class of A. I am putting this as equation 1. Okay. Now we prove the second part. So let I am taking an element y equivalence class of A. That implies that y related to A. So, but we also have that x related to A by symmetry property. A also related to X, and we have X related to A implies A related to X by transitive, by symmetric. So from these two conditions, from condition A and condition B, from A and B, is using transitive property, y related to A and A related to X. That implies y related to X, which implies that y belongs to equivalence class of X. So here I am taking an element in equivalence class of A and found that element is also belongs to equivalence class of X. So every element of this equivalence class A belongs to equivalence class of X, which implies that equivalence class of A is a subset of equivalence class of X. So from 1 and 2, it is clear that equivalence class of A and equivalence class of X are same. This proves the theorem. Okay, it is an important theorem on equivalence class. Now we have another theorem. Okay, the theorem states that suppose this denotes an equivalence relation on a set A. Now, for all A and B are elements of A, then if equivalence class of A not equal to equivalence of class of B, if and only if, then equivalence class of A is not equal to equivalence class of B if and only if their intersection is equal to. So we prove in a contrapositive method. So we take this is not equals and prove this is equal. So proof. Assume that intersection equals to phi. It's not equals to phi. That implies that there exists some x that belongs to the intersection, which implies that x belongs to both the equivalence classes and x belongs to, which implies that equivalence class of x is same as equivalence class of A and equivalence class of x is same as equivalence class of B. That implies since both are equals to x, so equivalence class of A equals to equivalence class of. So this proves our theorem. Now we have a definition. Okay, what is partition of a set? Partition means to break set into some disjoint sets. Okay, that disjoint sets commonly make the sets. Okay, so this definition states that a partition of a set is a collection of disjoint non-empty subsets of A whose union is E. So these disjoint non-empty sets, these disjoint non-empty subsets are called cells. Okay, and the cells are set to partition A. Okay. For example, suppose I have A, B, C, D, E. Then I have a partition of A as A, B, C, D, E. I can make another partition. That A, B, C, D. So this is all about partition of a set, and these are individually called, these are cells. Okay. So this is all about equivalence relation, equivalence classes, quotient set and partition, and we have done also two important theorem. So if you like and enjoy the video, please do subscribe and press the bell icon. Thank you.